All right, chapter 4. Chapter 4, we're going to take a look at another type of equation. So in chapter 2, we focused on quadratics and linear equations a little bit as well, but quadratics mostly in chapter 2. Chapter 3, we were focusing on polynomials, so we expanded things a little bit, and then at the very end, we threw in rational functions, which were ratios of polynomials. This is something completely different, absolutely completely different, nothing like the other pieces at all. So the first one we're going to do today in 4.1 is exponential functions. So exponentials, powers, is what we're looking at. And so just a real quick reminder from some of the things we did back in section P, chapter P. Powers, right? So we have 3 to the negative 2. What do negative exponents do? Say it louder for me, Tiffany. I think you're saying it right. They make it a fraction, right? So a negative exponent flips the fraction upside down. I know you're looking at it and saying, well, it's not a fraction, but anything can be written as a fraction, 3 over 1. So it takes the 3 over 1 and it flips the fraction to be 1 over 3. And then it squares things. We'll just put square down here. And what is 3 squared? 9. Okay, so negative exponent flips the fraction, and then we will use our powers to actually utilize those properties. What about the power 0? It makes things 1. What is raised to the 0 power here? Is it 4 or is it negative 4? Just the 4, right? So we have to be really careful not to inadvertently lose the negative. There is still a negative here. It is only the 4 to the 0 that becomes 1. So this is negative 1. And on number 3, you see that we have an actual fraction this time raised to the power. So just like on number 1, I'm going to flip my fraction. So this will be 3 over 2. That changes it to a positive 4 exponent, so 3 over 2 to the 4th. And then I'll raise each of those. This is a property of exponents as well, where I can distribute it to the numerator and to the denominator. Do you know what 3 to the 4th is? 81 is right. Good job. How about 2 to the 4th? 16. Lovely. This is 81 over 16. So we're going to see some of these properties at use, not significantly, but they will pop up from time to time. Exponential functions. So to start with, some exponential function details. I can't remember if I have a screen later. I do. Okay. So an exponential functions equation is f of x equals a to the x. There are some conditions on what a can be. A must be positive. Okay? So the a value itself is not a negative number. So we're not talking about things like negative 4 to the x. That'd not be okay. All right, but the 4 to the x would have been fine. We also have to have the case that the a can't be 1. And the reason it can't be 1 is because what's 1 to any power? 1. Right? It's a horizontal line. That is not an exponential function. It doesn't have any of the other properties. Now, in particular, looking at this equation and looking at those values, what happens is that the x values can take on any form. You know that they can be negative. We saw some negatives up there. You know they can be 0. We saw a 0 up in the review. And you know they can be positive because we can certainly take a number and raise it to the positive 3, right? So my domain for exponential functions is actually the whole number line. I can plug in anything for x. But whenever I take a positive number and raise it to the power, any power, it will always stay positive. It's much like our square root functions, right? You take the square root of something that you're allowed to take the square root of in the real number system, it's going to be a positive number. Right? Square root of 5, well, it's an ugly number, but it's positive, right? On this one, if I had 2 to the 7th, 2 to the negative 7th, 2 to the 0.7, 2 to the 0, doesn't matter. It's still going to be positive. So my range gives me only positive numbers for this function. Now there's a couple of graphs that go along with these that we're going to take a look at on the next slide. Are these okay? All right. There's actually 2 possibilities with a being positive. One possibility is that it's positive and it's bigger than 1, right? It's a bigger number than 1. The other possibility is that it's somehow between 0 and 1. So think like fractions and decimals that are small, right? Like 1/2 or 0.7, right? Numbers that are between 0 and 1. And the graphs that come out of those are slightly different. They both actually cross this axis here, because if you take a number and raise it to the power of 0, you get 1. But if your graph has a value that is bigger than 1, it looks like this. And if the value is between 0 and 1, it looks like a reflection of that. And they're reflections of each other. I already made mention that the y-intercepts are the same. The y-intercepts in both cases are 0, 1. Because if x is equal to 0, and I plug 0 into a to the x, I get back 1. Can you tell me what the horizontal asymptotes are from the graphs that I've drawn? Okay, so an asymptote has to have x equals or y equals?
Y.
It's y equals 0. Both of these have asymptotes, horizontal asymptotes, at y equals 0. Right? There's a line here that I'm getting really close to on one edge, not both edges this time, but on one edge, and I'm not crossing. There is a horizontal asymptote there. But do you remember back in, somewhere in chapter 2, and we did some shifting of graphs, where we shifted them left and right and up and down, and we reflected them over the x-axis, and we reflected them over the y-axis, and we stretched them all out of shape. Do you remember doing all that? Yeah? We can do that with these functions too. So when you look at this graph, those are the kinds of things that you now see happening. So this is speculation. So if you're wrong, it's no big deal. We haven't talked about it. Speculation. What do you think the +1 on the end might do to such a graph? Say it for me, Brooklyn. Move it up 1. You're exactly right, because that's what it did before, right? You add something on the end, it moves it up. You subtract something on the end, it moves it down. So this is going to be a shift up 1. There's a negative happening inside here. The negatives are a little trickier. Negatives create reflections, if you remember. So you have to be a little more careful. Does it reflect over the x-axis, so like up-down reflection, or does it reflect over the y-axis and reflect left-right? Which one do you think it is? It's been like a month since we've talked about this, so. It's a 50-50 shot. Which one do you think? You think it's x? So reflecting over the x-axis, so like this, right? You're exactly right. It is. So if the negative is embedded inside with x, it flips over the x, or it flips like this, across the y equals 0 line, across like this. So this one right here is we call it a horizontal flip. So a horizontal flip affects x values. All the x values that were negative are now positive. All the x values that now are positive are now negative. If it had been a vertical flip, you would have actually seen the negative happening on the outside, much like our vertical shift of going up 1 happened afterwards on the outside. And the last thing that we didn't have happen here yet, but we do in a moment here, like this, is we have a number where it's subtracted inside with x, and that's going to be the shifting the left and right, which we'll get to in a minute. So I'm supposed to have a horizontal flip. I'm supposed to shift it up 1. And then I'm going to identify these 4 pieces of information, namely the new horizontal asymptote, which may or may not be the same, the y-intercept, which may or may not be the same, and the domain and the range, which may or may not be the same as the original graph because I'm shifting it around. So I think it's a good idea when you draw these, even if it's a light sketch, to kind of sketch for yourself what the original graph looked like. So I'm going to try and draw it as thin and small as I can. The original graph for 3 to the x looks something like this, right? It does. So this is the image that I'm messing with. We're going to work from the inside out, and on the inside it talks about the flip. So the first thing I'm going to do is I'm going to take the graph and I'm going to flip it around the y-axis. I'm going to flip it horizontally. So this graph, I would wish there was like a rotate tool. It'd be really cool if I could just rotate it on my screen like that. There's not. So the next thing I'm going to do is I'm going to rotate it. So now the graph actually flips around and looks like this, which is very interesting because that's actually like the other graph, isn't it? There's a reason for that. I'll mention it in a minute. Okay, so it's flipped around. And then how does it need to be shifted? It needs to go up 1. So we're going to take the whole graph. That I can do in one fell swoop. I can shift this whole graph up 1. Well, I almost can. I can only do one end at the same time, or I was going to catch both my graphs. If it bothers you now to have this listed in here, you could certainly like erase it if you've drawn it, small. Here's the number 1. Here's where it's crossing now at 2, because it shifted up 1. And while I didn't originally draw it in, the original graph had a horizontal asymptote at the x-axis right here, right? And so when the graph got shifted, the asymptote should be shifted as well. So it should have also been shifted up 1. So this is my new graph, all the details in place. Notice we don't have a lot of specificity. I don't have how steep this is. It's not like, is it really tight and narrow, or is it really broad and wide? That's not what we're working with. Those aren't the details that we're focusing on. So you kind of have some flexibility on that. What is my new horizontal asymptote? Okay, so remember, x equals or y equals? Y equals. Y equal 1. What is my new y-intercept? Where is it crossing? It's the only number on my screen, guys. Somebody say it. 2. Thank you. Specifically at x equals 0, y equals to 2. That's my y-intercept. What's my domain? Domain x values. If I move from the left to the right, what x values am I allowed to use? All real numbers, right? Negative infinity to positive infinity. However, my range, I don't have everything. There's a whole bottom half of the graph-ish, whatever, that I don't have. So as I'm sort of climbing my way up my y-axis, where do I first start seeing values almost? At 1, yeah. And not quite at 1, right? Just right after that asymptote at 1, all the way up to infinity. So my range is 1 to infinity. Minimum things you need to have plotted are exactly the things I've got shown here. The intercept, right, a specific point. We might actually shift our intercept here in a moment on a different one. And that asymptote, and then the graph's shape in general. I said I would tell you this, so let me actually mention it right now. The reason that this ends up looking like the other graph is because 3 to the negative 1, as you know, is actually 1/3. 1/3 means the graph ends up being in the right-hand category because it's a number between 0 and 1. That's what that reflection does, is it actually turns it into a fractional piece. Okay, so that's why it's happening. All right, what is this negative 1 going to do in terms of my graph? Yes. So it's going to shift it to the right 1. And how about the negative 4? Yep, down 4. All y'all's voices disappeared over the last couple days. I can just tell they're not working. Okay, so one thing you could do, if you wish, instead of drawing the original graph, although you could still do it. So the way I did it before, where I drew the original graph and then I shifted everything around, that's totally one way to do it. Another way to do it is to simply move the location of like a specific piece around. For example, normally our graph would cross at a y-intercept right here, right? I could actually just move that point and the horizontal axis or asymptote around to reflect what's happening. Obviously, the horizontal asymptote moving left or right doesn't change anything, but the horizontal asymptote moving down definitely does. So I could move my horizontal asymptote down 4. And that would make sense. I could also take my point, which was here, and I could shift it the way I've described, moving it right 1 and down 4. So if I move it right 1, it would be here-ish. And if I move it down 4, it ends up down here. So I can move those specific location. What is the general graph supposed to look like? Is it supposed to be an increasing graph from left to right, or is it supposed to be a decreasing graph from left to right? It's an increasing graph because it was 3 to a power, right? 3 is bigger than 1. It should look like the first graph on this screen. So my graph should go through the point that I plotted, not this one up here. That's not a point I plotted. That was my moving point. But through that point that I plotted down here at 1, -3, and it should go up on the right and down to the left. This is my basic shape. What's my horizontal asymptote? Yep, y equal -4. The y-intercept's a little more difficult. We'll come back to that in just a second. How about my domain? All real numbers, -infinity to infinity. And what about my range? -4 to infinity. Great job. Okay, the reason I say the y-intercept is a little more difficult is because it's not the point that I shifted, right? The point that I shifted got moved over here to 1, -3, and it's somewhere crossing between the -3 and -4, but I don't know an exact value at the moment. Agreed? So in order to find the y-intercept, I have to actually do it the way that I was doing it before, where I plug in a number for x. So namely, the y-intercept is when x is equal to 0. So I have to take this equation right up here and put x is equal to 0. So y is equal to 3 to the 0 minus 1 minus 4. Well, 0 minus 1 is -1. 3 to the -1 is 1/3. 1/3 minus 4 means I need a common denominator, so like 4 over 1, which would be the same as 12 over 3. I don't want 3, I want 4, sorry. 12 over, so how about 16 over? No, I do want it over 3. Sorry, the 4 was just throwing me for a second there. 12 over 3. Okay, right. So then if I have 1 minus 12 over 3, I would have -11/3. You can write that down, that's fine if that bothers you because it doesn't have a concrete sort of picture in your mind. This is -3 2/3. That's the value. So my y-intercept is x equals 0, y equals -11/3, or -3 2/3. Any questions on that? Okay, so we're not going to finish, but we do have time for at least one more example. So what that means is that I would encourage you to do everything graphing related in this section before Tuesday, because otherwise you're going to have a really lot to do between Tuesday and Thursday next week. Okay, but we'll push this section back. I'll get it done respectively in Canvas like that as soon as I get back to my office. So let me show you a couple things about exponential equations that are helpful. Equations 6 and 7, or problems 6 and 7, are equations that we're going to solve. We're trying to figure out what x value does certain things. And in particular, as we are doing this section, our goal is going to be to get both sides to have the same base and then compare their exponents. That's our goal. Same base. So on the left-hand side, we've already got a 2 to the x, right? There's nothing else I can do about the fact that, there's nothing else I need to do to simplify that fact. It's already a base of 2. I do realize that these are both negative, so I could cancel the negatives out initially, just divide or multiply both by -1. So now I have 2 to the x, and I want the other side to have the same base. How could I rewrite 1/2 so that it's 2 to a power? 2 to the -1, exactly. So this is really my goal. This is a very simple one to start with. You might have looked at it and said, I just know the answer to start with. Okay, fine. But you're not always going to. The next one is a case where you probably don't have the ability to just see it. 2 to the x, 2 to the -1. Once they have the same base, we just set the exponents equal to one another. X equals -1. That's our solution. If we got to that point and we had more going on, we might have to solve it. We will do that on number 7. On number 7, the right-hand side is already just a plain old 2, like a 2 to the 1. I need the bases to be the same. How can I rewrite 8 so that it's 2 to a power? 2 to the 3. And there's an x, that looks like 23, sorry. 2 to the 3. And then there's an x on that. So some of you are already telling me it's 2 to the 3x, and you're exactly right. Equals 2 to the 1. That's my goal. Same base. Once the bases are the same, I compare the exponents. I set the exponents equal to each other. Notice I didn't cancel any bases. I'm just ignoring them. If they're the same, they're irrelevant to the problem. So this is 3x equals 1, and what would I do to solve for x? So on this one, x is actually the number 1/3. The last bit of questions inside of this section have to do with interest. Okay, they're word problems. Yes, sir.
If we were to recognize that it would be x to the 1/3 at the very beginning, do you have to still work out the whole problem?
Show me some of them because I want to make sure that you know how to do the process, not specifically for this problem, but for other problems that are more complicated. Does that make sense? It's always a catch-22 on giving you something that's complicated enough that you have to show me something, but not so complicated that I overwhelm you and you don't try, because that's not a good idea either. So I try to balance it, but it doesn't always work out that way with what I'm presented with. So when we come back next time, the only thing that we haven't done in this section is word problems. So you should be able to do the homework up into the word problems section from what we've done in class.